Hi guys, I'm Prof Joe and this is part of my lecture about measurement technology, dealing with chapter 2, digital technologies. Today talking about analog to digital converters. Last time in the first part of this chapter we talked about the digital to analog converters, and now we will do the way around, the other direction. First step for that conversion is a sample and hold circuit. Just sketching a simple one. It consists of two impedance amplifiers, simple amplifier circuits. Just watch the video about those amplifiers to get to know about those. Having one capacitor and again a second impedance converter, which produces the output, or which gives us the output voltage. So why using that thing? Sample and hold. The idea is quite simple. When we want to convert an analog voltage to a digital number, we need that analog voltage to be constant over a certain time at least, but at least long enough so that the upcoming AD converter is able to convert that voltage as a constant voltage. Why should it be constant? Because having a changing voltage during conversion will produce, as you are expecting, also strange results, not reproducible results, and so on. So the first goal is to just hold the analog input voltage over a certain time. And that sample and hold circuit can be used for that. Looking at it, we get that input voltage UE, which also just is reproduced over here behind the operational amplifier. Then there's the switch, and now let's assume the switch is closed. That current, that voltage UE will be used to load that capacitor over here. So that capacitor will get, for a closed switch, the same voltage as UE. Now, reopening the switch, the capacitor will try to deload again, not able to deload across the open switch, but able to deload a little bit across the operational amplifier, but theoretically, for the ideal operational amplifier, also not able to deload across the operational amplifier, so just holding that voltage UE for a certain time. And now that voltage UE again is reproduced at the output of that second impedance converter, impedance amplifier over here. So what we get is the same voltage coming in here is reproduced at the output. That's great. And we are now able, by opening and closing that switch, to hold a certain voltage over a period of time we can define by the time which the switch is opened. So by that we are able to make discrete time intervals, to have a discretization of the time, sampling over the time. That's where the sampling comes from. And that introduces some additional features or errors or whatsoever, meaning when converting an analog voltage over here, we typically have several stages where the sample and hold circuit is in between. The AD conversion is at the end, and at the beginning there's an additional filter, an anti-aliasing filter, which means that by sampling over our input analog voltage, So by using that sample and hold circuit, we introduce problems by sampling over time, and that sampling is not able to reproduce the details in time of that analog incoming voltage, meaning we are restricted by the sample theorem to convert voltages which have frequencies which are 2 times lower than our sample frequency over here. That's at least interesting to know. The idea is quite simple for anti-aliasing. It's that whenever there's a, for example, sine curve, and we sample some points of it, you always could guide through higher frequencies hitting exact the same points. And what that means, 2 high frequencies coming in here would be interpreted as lower frequencies due to the fact we are not sampling fast enough. That's the reason for that filter over here, filtering out 2 high frequencies, we are not able to distinguish anymore. Okay, now the sample and hold circuit gives us time discrete voltages in time discrete time intervals. And now that voltages, those constant voltages, can be converted by an AD converter circuit. How does an AD converter work? To be honest, we already know everything what we need by talking about DA converters in the last chapter. Why? Because DA converters give us analog voltages. And now we know a circuit, operational amplifier circuit, which allows us to compare voltages, the comparator. And now the first and most easy idea of converting a voltage is to use a bunch of comparators which give us a digital encoded number which has to be decoded. We'll see what that means in more detail. And which just compares an input voltage. So let's assume here's our input voltage UE, which is connected to the operational amplifiers to reference voltages. So, for example, we could produce different reference voltages by just introducing and so on, and connecting the different parts to the comparator. So that means we have a reference voltage which is split up in different parts which give us different voltages at the different points where the comparators are connected. And now each comparator compares the incoming voltage to a different voltage by that circuitry, and by that switching, for example, at that point over here, very easily, because it's a low voltage which is applied, which is the compared voltage to compare to, and which lets the comparators down here switch later because the voltages are higher compared to. Now what we get is not a digital number in the dual system, but we get some digital thing we can think about in logics using XOR circuitry and so on, which can be decoded digitally. So there's a digital circuit which can interpret the input given by those comparators over here. That's obvious, an easy way of converting an analog value to a digital number. Just comparing the incoming voltage to different given known voltages. By that, being able to produce a digital number just by comparing. So that's the main idea of any AD converter, comparison. What's the problem about that thing? Each recognizable voltage step has to have its own operational amplifier, and those are a lot. So that's not ideal. But we know something which can give us reference voltages in an easier way. Thinking about DA converters, that means we could just use a DA converter as reference voltage, replacing that series of resistors and the reference voltage. And now that thing again just is compared with a comparator which is on the other side connected to our input voltage. Now we can set up a certain voltage and compare it to the incoming voltage. And now how we set up that voltage, we do some logic with the successive approximate AD converter, giving it the name it has and giving us the digital number. How does that thing work? Easy said. Let's assume we have a 4-bit number, or let's assume we have a 4-bit number, and let's say for example, just to have an example, we want to convert a voltage of 9.5 volt and have steps of 1 volt, 2 volt, 4 volt, and 8 volt to match those 4 bits. Now, what is done? First thing is let's sketch. So here's the voltage, and here's somewhat the digital numbers. And now our input voltage should be 9.5 volt. And now let's assume we are starting conversion, and the idea now is to switch on the highest bit we have, and that's the 8 volt bit, and watch what the comparator tells us. The comparator tells us, man, the input voltage is higher than the comparison voltage you give me. Telling us, okay, we get a 1. Now, switching on the highest bit and now the second highest bit. Adding to those 8 volts, 4 volts. And now what you see there, the comparator will now tell us, man, the voltage I compare to is larger than the incoming voltage. Meaning that's somewhat not okay, resulting in a 0. Now keeping those high bits means we have 8 volts, and now switching the third highest bit will add to 8 volts 2 volts. Still being higher than 9.5 volts, telling the system we need a 0 over here. And now switching on the 1 volt bit. So here's 8 volt, 4 volt, volt, 2 volt and 1 volt. And now that 1 volt bit will result in a voltage somewhat a little bit below 9.5, namely being 9 volt, and that will give us again a 1. And what we get, you see over here, is the digital number by doing one switch circuit for every bit, meaning for 16 bit, we need 16 cycles. Over here, we need 1 cycle, assuming that the decoder works within 1 cycle, because there's a comparator for every voltage. Over here, we need, for every bit, we want to know about 1 cycle. Meaning that thing over here, presumably, is faster, because we only need 1 cycle, but needs a whole load of operational amplifiers. That's problematic. Over here, we don't need that much operational amplifiers. Indeed, the circuitry is quite easy. Think of the circuitry of a DA converter. That's not complex. Comparator, that's not complex. The most complex thing is the digital logic of that successive approximation unit over here. But indeed, talking about digital circuitry, that's not a very complex digital circuit we have to think of over here. So it's a simple thing, and it gives us the possibility to convert analog values quite fast, not as fast as a flash converter. This one is flash converter. It's called a flash converter. And this is the successive approximation converter. It's not as fast as this one, but has the ability to build higher resolutions much more easy than the flash converter, because just think about a 10-bit flash converter over here. We would need more than 1,000 comparators, and we would need to combine those in a circuitry which deals with resistances of the resistors themselves and the resistances of the connection in between the resistors, the voltages, and the comparators. That's a complex task. Over here in the digital part of the circuitry, that's no problem. There's a 1 and a 0, and now if that circuitry is long or short, or there's a resistance is not very exact, that's no problem, because it's not about the exact value, the analog value, but only about the digital value. So over here, that's an easy circuitry. Over here, that's a complex circuitry, because we have to deal with all the resistances. Okay, there are more converters, of which one has to be named. Mostly used in DA converters is the successive approximation converter, as we see it over here, or the so-called delta sigma converter, which is based on a different principle than the successive approximation converter, because it produces not a digital number itself, but a bit stream, which converts, or which describes the value of the analog input in the distance and the switching times between 0 and 1 at our output, which indeed can be converted digitally into a real digital number. Not showing the detailed circuit, just ask the AI-Tutored to give you a detailed circuit. The idea of that delta sigma converter is to integrate over the incoming voltage in comparison to a reference voltage. Now that reference voltage switches all the time, so we get an integration which normally looks like that, when no voltage is applied externally, and now when a voltage externally is applied, that reference switching between plus and minus uref, let's say that's plus uref, that's minus uref, and integrating over it will be switched in a certain direction, meaning when uref is reduced, the plus way will be, the plus slope will be slower, and the minus slope will be faster, and so on. And by that, giving the possibility, connecting that signal to a comparator to get a cycled, a bit stream signal looking somewhat like that for a 0 voltage and like that for a certain higher voltage. But that's just the idea. The advantage of this delta sigma converter is not that it's very fast, because you see there's some timing involved in the whole working scheme of that AD converter, although it's fast enough. But being able to convert in respect to the digital number as exact as we want to, because we just can increase the timing of that integration over here, and by that making the ability of switching more distinct, faster, more detailed, and by that increasing the digital resolution of the system just by increasing the speed within the conversion scheme we just looked at. Yeah. Talking about the successive and delta sigma converters, those are the most important ones. Whereas the successive approximation converter is a central AD conversion unit, which can be quite fast and which can be quite, or which can have quite high resolution, being usable, very flexible. Whereas those three types I've shown over here, there are much more different AD converter types out there. There are pipeline converters whatsoever. Just combining different techniques of those conversions, or for example combining 4 successive approximation converters to increase the speed, and so on and so on. So there are different ideas of AD conversion we won't go into detail about. Thinking about AD conversion now simply as the comparison of a reference voltage to the unknown voltage, and by that getting to know about the digital number equaling to that unknown voltage, because we know the digital number of that reference voltage. That's the main idea. We know the number of the reference voltage. Now we compare that to the unknown analog input voltage, and whenever there's some switch, we know that digital number we know for our produced analog value equals to the input voltage, or the number of the input voltage, the digital number of the input voltage. Okay, having talked about those AD converters, that's the end of the second part. The next part will be about some general talking about working with digital signals, working with digital measurement instruments, and so on. To round that up, the whole chapter, not giving you much details about all that large area of working with digital signals. If you like that stuff, feel free to subscribe, and see you next time.